cherry-pick through some of his bio. Bob and I first have worked together since about, I guess, 86, 87, when UNAVCO was first formed, and Bob is one of the people who's responsible for helping to get the consortium going, and also was primarily one of the principals in getting the IRIS consortium going. So I think that experience with IRIS helped pave the way for the geodetic consortium like UNAVCO. And so some of the first work that we did at UNAVCO was with the TI 4100, and if you haven't seen it, it's out in the front. And if you've used it, you probably have still a sore back, and I think Bob can attest to that. Many of us here worked on his campaigns, and that was the Yellowstone work started in '87 and repeated and did some of the work, first work on the calderas of Yellowstone, and we're going to hear some of the most recent work with it that continues with EarthScope, which Bob was also involved in helping to start. So it's a long legacy of working with our community. And I think some of the key lines I think that I like to draw on here is that he's always strived to teach and educate students, government officials, and the public on earthquakes and volcanoes. I think if you know Bob, he's in some of his work, he's always worked hard to educate, like, for example, the public up in Yellowstone, and some of the new visitor center highlights, even GPS. And some of our equipment is actually in the visitor centers. And I think another interesting quote is that his initial studies in Yellowstone started in 1956 when he was in a field course, and then in '59 experienced the 7.5 earthquake in Hebgen Lake. So if you've ever been through an earthquake, that actually was what I was just talking about this morning, is the '71 earthquakes that got me involved in earthquakes and studying the Earth. So I think that sometimes you have these defining moments. And Bob actually got his PhD at University of Utah, where he's a professor. He has, over his career, taught about 200 classes. He has had about 68 masters and PhDs, some of us in the room. As postdocs, countless postdocs. I don't know how many postdocs he had. And at one point was actually a pilot, a jet pilot in the Air Force. And I thought this was interesting too. You were an officer in the geodetic and geophysics officer, which I've never heard of, but it sounds like a great position. It got you going. So rather than go through any more of these many pages, I'll give Bob the mic. Thanks. And you've got one.
Right. Oh. Yeah. It's fun to come back here. A lot of people that I know for a long time, including Craig now, saying hello. And it's fun to come back periodically and see how the organization is growing and meet people and give you ideas of how the things that we're doing have been growing as well. And today Chuck asked me to give this presentation, so I called it, past, present, and future, but the second line says, or why it's always uphill to Yellowstone. And that happens to be very true, dynamically and topographically. I'm going to talk a bit about, the Yellowstone history, geologic history, views in the past, talk about earthquakes, Hebgen Lake, something about kinematics, using GPS, among other things, and then dynamics and how we integrate information. I'll end up discussing some new work on hazards and risk, where we integrate all the information, and I'm going to show you some view of our latest findings. I do want to mention, these are the organizations that have supported me during my career. This is our research group at University of Utah and seismograph stations, University of Utah, for all of our earthquake recording and GPS recording. We've worked closely with the Park Service since day one, and a very close relationship and very positive relationship. NSF has been our long-term funder, and we appreciate their support. They funded us in the beginning of our studies in the 70s. And of course, EarthScope now has come into being as a result of a lot of people's efforts here. And the whole idea in EarthScope is to integrate information, so I was instrumental in helping get this organization going. The USGS is heavily involved with us in a cooperative nature. We're part of the Yellowstone Volcano Observatory. And of course, UNAVCO has been supporting us since the day one of our GPS work. We have a couple of private foundations that also fund pure basic research, for which we can't get money anymore from the federal government, right? And we can go to foundations and these folks to really recognize, and I have to say, these people have been very instrumental in our projects. By the way, you can't apply to them, they apply to you. I am. That's not going anywhere. Say again? Here's I want to let you know that people make up the projects in Yellowstone, besides the fact we do and have great science. And I want to really acknowledge there's several people who have worked with me for many, many years. In our seismograph network operations, there's 2 FTEs, but the principal one is David Drobeck, our full-time engineer, does GPS and seismic, and Ken Whip, his colleague. They go out in the field, service instruments, and this is our brand new recording facility that we just built at the University of Utah. Other personnel, there's roughly 3 FTEs. Jamie Farrell's a senior PhD student defending in about 2 weeks. Other people you may have heard of, Greg Waite, Jason Crossway, who are installing seismographs, broadband in the south end of the park. Here's Christine Puskastar installing a GPS in the Teton area. And then our collaborators are quite varied. Park Service people, USGS, Gene Humphreys and I at the University of Oregon worked together a long time, Southern Methodist University, Swiss Federal Institute of Technology provided a lot of support for geodesy and gravity, and Harvard folks, principally with Volcano, we're working very closely with. Here's Hank Hessler, the park geologist. He's a PhD in geophysics, actually, and is very savvy about thermal problems in Yellowstone. And this is his staff that also support us in terms of USGS. And I have to recognize the person, Rick Hutchinson. Most of you won't know him. He was killed in 1967 in an avalanche on Mount Sheridan. But he worked many, many years with us, and here he is learning how to operate a GPS system at the Utah dorm. So Chuck will, of course, remember him well. So we do have a very dedicated staff of people that work very hard in our system. But this is the epitome of Yellowstone, beginning in 2004. Before 2004, Yellowstone was just another big national park, you know, and it had lots of animals. Yeah, there was geology and geysers and hydrothermal systems. BBC folks came out and made their documentary, and they titled it Super-Volcano. And you can see from the slide here that it was a very dramatic presentation. And we were all consultants, by the way, on it. And what they said was not wrong. They actually were very careful in their production and in their preparation and their writing. It's just that they made the imminence of a super-eruption right now. So they really exploded up the hype around the potential explosion, and they got the whole world thinking about Yellowstone as an active volcano. So in the overall sense, I think they did us a lot of good. Now, I always remind people that Yellowstone is not out in the middle of the Pacific Ocean in Hawaii or the middle of the Atlantic Ocean in Iceland. It is right here in the continental interior. And this is a slide I've made up when I've given the presentations, as a matter of fact, for the National Science Board for the funding of EarthScope. And the position was, Yellowstone is the basic, contains all the elements of plate tectonics, and it's accessible. So there's a transform fault in California. There's an active subduction zone, Pacific Northwest. We have lithosphere extension in the Great Basin, and here is Yellowstone hotspot. Now that's something that actually a congressman or people in the National Science Board appreciate, because they wanted to say, how do you fit Yellowstone into plate tectonics? Well, it's the only major continental hotspot in the globe, and so this is the slide that captured their attention in one of my presentations. The other thing I want to impress upon you is that I like to work in different fields, because I think you have to work in an integrative way. And I'm going to start out by showing you a tomographic image of a mantle plume that goes from about 80 kilometers. I'm going to show you the new one that goes 1,500 kilometers. This is our image to 700 kilometers. It feeds magma, which goes into the crustal magma body, and I'm going to show you some new data on that. And this is the shallow body, 5 to 10 kilometers deep, and we get heat, hydrothermal fluids, magma that drives Yellowstone, volcanism, and of course the deformation. And here's an INSAR image during the period we had the caldera accelerated uplift, which I'll talk more about. The point being is these things are all fitting together. So in my story, we have a magma chamber fed by the mantle plume. We get ground deformation related to fluids coming off the mantle. Earthquakes are driven by both. Hydrothermal features, of course, driven from the magma and the heat. That's the Yellowstone volcanic field. If you look carefully, these are all double arrows. And what that means, everything is fitting to everything else. You can't just take one and study it, think you're going to learn something. You'll learn a very narrow amount compared to the integration, and that's what we've tried to work hard on. Now, this gentleman, Lieutenant Doan, came into Yellowstone in 1870, and if you ever heard the Doan Expedition, it's a wonderful read. He came in from the north side of Yellowstone with an expedition in late fall, made a boat, went down Yellowstone Lake, visited the canyon, damn near died when it started to snow and the Snake River froze up. Eventually got out late in December. But here's what he says in his memoir. As a country for sightseers, it is without parallel as a field for scientific research. It promises great results in geology, mineralogy, botany, zoology, and ornithology. He was not an ecologist, but that's the definition of ecology. And he says it's probably the greatest laboratory that nature furnishes on the surface of the globe. That was a pretty prophetic statement. Yellowstone has its roots in the sense of a volcanic system. It's a silicic volcanic system, and I'll start here by showing in yellow the areas surrounded of giant centers, much like Yellowstone. 16 million years ago, 14, 12, 11, 10, 6, 7. Of course, you realize we're getting progressively younger to the northeast, and that's moving over an upper mantle source from the northwest. And that's moving at roughly 2.5 centimeters per year. The surrounding zone of high topography, active faulting shown by the black lines, that we, in this case, the contemporary seismicity shown in red dots, which we've named now the tectonic parabola. Well, we named it quite a while ago. And the question is, what is this? And more importantly, what are the dynamics that create it? Because it's like a bow wave in a boat. This is a bow wave in lithosphere. So the North American plate is moving through a plastic lithosphere, and this is the type of resulting pattern that we believe that it left, and we think this gave us the real key to the linear or the variation of temperature or age and the very low elevations along the track of the plane due to contraction and cooling of the lithosphere as the volcanic centers occurred. Now, by the way, from here to here, there's probably 150 supervolcanoes. So each one of these contains, like this one right here, has 20 original Yellowstones. This is work done by Mike Perkins doing tephrochronology, and he's mapped the whole system. Well, we go immediately to Yellowstone, and the green, of course, is Yellowstone Park. Orange is kind of caldera number 1, and it formed around 2 million years ago. And caldera number 2, this one over here at Island Park, formed 1.3 million years ago. And finally, in red, we have caldera number 3, which we call the caldera, 640,000 years ago. So this gives you a historical perspective of the youthfulness of the Yellowstone volcanism and the size of these calderas. This one is about 80 kilometers long. This one is a good 120 kilometers long. The inter-event times are what are important. So you see there's 2 inter-event times from the oldest to the next to the oldest. And the time since the last event, 640,000 years. The average of the 3 inter-event times, 710,000 years. And this is the one you have to debunk all of the hype that Yellowstone's ready to blow up again. Because, number one, if it's 710,000 year interval, we're still 70,000 years away. But I don't believe any of that because the statistics of only 2 numbers, this number and this number, are infallible. Infallible in terms of understanding the estimate. So we have no idea where we are in the cyclic nature of these super eruptions. But I've given this to the Park Service, to their interpreters, and to CBS and ABC, hoping that they will use these ideas and concepts right, that we do not know the state of cyclic deformation of these giant systems. Now, in my book, I hypothesized, with the help of a lot of geologists, atmospheric physicists, and petrologists, et cetera, what one may have looked like. And this is looking south into where the Tetons would be back here. This would be on the upper Lamar River country on the northeast side of Yellowstone. And what people now think is that the super eruption formed this 640,000 year event probably started as a series of ring fractures, or erupting out of a ring fracture zone, and that ring fracture zone developed, lost its support, dropped the caldera roof, then eruptions occurred across the entire caldera lid. Ashes and gases probably, we know, rose to at least 80,000 feet, and once they're at that height, they're trapped in the jet stream. And we know now from latest studies, just published recently, that this system probably took years to form. It's not instantaneous. So you can't get out 3,000 cubic kilometers of magma kind of like in one shot. So these are long-lived things. Over in geologic time, they appear short. But the important feature in terms of climate, the temperatures I notice here, from the atmospheric SO2 and the aerosols reduced the temperature by 9 degrees centigrade, probably going on for decades, and this was used by recent volcanologists to argue for volcanic winters, and the Yellowstone was a key one, and I won't go into that. I have another set of slides that describes that, but nonetheless, it was a profound global feature. So here's a relative scale showing the volumetric release of Yellowstone here on the upper right, compared, here is Mount St. Helens, 0.3 cubic kilometers. Here is Mount Pinatubo, 2.4 cubic kilometers. Pinatubo is in the Philippines. Krakatoa, you've all heard about, 1883, 4 cubic kilometers. Mount Mazama, the heart of our national park in Oregon, 7,000 years ago, 18 cubic kilometers. And Tambora, another giant Indonesian system, as you can see, 36 kilometers. Well, here's the smallest of the Yellowstone systems. That's the Island Park caldera, 67 cubic kilometers. And then the next size is the latest 630,000-year-old feature, 240. But the big one at essentially 2.1 million years, 600 cubic. I've got miles and kilometers mixed in here because I've written a book by Oxford University Press, through their auspices. I have to use miles, and I go back, but I think in kilometers. So sorry about that. But you can figure it out and see the relative proportions. This is the known distribution of the ashes. Huckleberry Ridge Tush is this darkest tan here. That's for the big one. And then lightest tan is for the most recent 600,000-year eruption. And Mount St. Helens, just for scale, of course, it dropped ash over into Yellowstone that was a millimeter thick on our windshields. Since I made this slide up for my book, we now know that the ashes probably covered the entire United States. They're well recorded in cores from the Pacific, from the Gulf of Mexico, and from the northern Atlantic. So it has a much more profound effect. Well, Yellowstone is an interesting place. This is the Yellowstone Park boundary. And as you can see on this DEM over the topographic map, it's a relatively flat, high mountainous plateau. So when I drive up from my home in Moose, I drive up through Teton Park, and I take a lot of guests up. We get up here toward West Thumb. We've had these grand views of the Teton Range here. We get up to West Thumb. The first question is, where are the mountains? Well, the mountains are gone because they were destroyed by these giant eruptions. And in place, we have this high mountainous plateau that's about 1,500 feet in average elevation above the background topography, and I'm going to show you that we argue that is the effect of the hotspot buoyancy. And you can see all these other mountain ranges, such as the Red Mountains here, Chicken Ridge, they all terminate and are cut off on what is thought to be the boundary of caldera number 3, including over here on the north side. So this is a high mountainous plateau. The Absarica Range are 45 million year old basaltic breccias, and they're not really part of the hotspot story. If you drive in from West Yellowstone to Madison Junction, right here, and you want to go, this is the road, for example, toward Old Faithful to the right, and there's a big wall right here. That wall is the fault from the collapse of caldera number 3 as it collapsed back into the system. What's more important, you can't see this from the road, but Mount Holmes is this end of the Gallatin Range. This is Mount Holmes. It was cut off abruptly by caldera number 1. So these calderas, of course, develop these large topographic plateaus and then collapse as they lose their roof support, and they are very, very large. And if you drive up the Firehole River over here on the west side, and if you go to the parking, how many go to the parking lot to swim? Oh, I know Chuck does. You park there, there's this great swimming hole in the Firehole River, right? You weren't doing your science. If you just walk back 10 feet, there's what you see. So these are breccias of rhyolite, andesite. Some are mixed in with andesite, but it's dominantly rhyolite, tuffs, and breccias. And you can see the angular nature of these systems right here that have cooled relatively rapidly. Here's some bigger features. Some here, float out like pancake batter. Now, why is this important? Well, first of all, it's rhyolite, it's not basalt. It's important because basalts are about 1 million times greater in resistance to flow. We call it viscosity. So they're 1 million times more viscous than basalts. So when you go to Hawaii, the nice volcanic flows just flow down the street and the road. In Yellowstone, these things don't flow. They flow very short distances because they're so viscous, and if they're so viscous, they're not going to move. They trap the gases, they trap the magma beneath them, and when they finally go, they're explosive. So Yellowstone's volcanism is more explosive than the runny basalts of Hawaii. And if you go down to the southeast corner of Yellowstone, you can see some of these big flows. This is into the Beckler system. These are flows coming off Pitchstone Plateau. And this is up toward Old Faithful. This is a resurgent dome. Touch of snow that day. A resurgent dome is basically a dome of topography that's held up by a magma body at depth. You can think of it as a piston pushing the ground up and the sides dropping down. There are 2 main resurgent domes in Yellowstone. This one is just north of Old Faithful right here. So if you take the height of Faithful, we'll go to Mallard Lake where we have a GPS station. How many here have been to the Mallard Lake GPS station? You're on the resurgent dome, and the resurgent dome has shallow magma beneath it. Well, again, I go back to these early studies, and this same Lieutenant Doan was over on the east side of Yellowstone, and from the overlook, right to the east side of the lake, and he says, the entire basin may be obtained with mountains surrounding it on every side. The Great Basin has been formerly one vast crater, one extinct volcano. It might be called one vast crater, one for which fluid, material of the earth, fragments, etc., are poured of the quantity. So this guy Doan had a great perception of what Yellowstone was about. And the reason is, this is the edge of the caldera sitting right there. So that side dropped down, this side stay high. And in the background, you can see Mount Washburn over here. This is the Black Elephant-Back Fault Zone that connects the north side of this resurgent dome with the one I just showed you. Well, hydrothermal features are the icon of Yellowstone, and I've put here a figure showing everything, fumaroles, hot springs, geysers, and you can see that they're dominantly within the outermost fracture of the caldera with a zone up near Old Faithful, lower geyser basin, and then stringing on down along this corridor, which is outside the caldera. We call it the Mammoth Corridor. This is North Geyser Basin down to Mammoth Hot Springs. But I want you to pay attention right here in your mind. This is the northeastern side of Yellowstone with the biggest hot spring system, the biggest hydrothermal system in North America. It's called Hot Springs Basin. Now, it doesn't have it. I'm going to show you a picture or two of it. It doesn't have geysers. The reason it's such a high hydraulic head, it's almost 8,500 feet. But you can see the size. It extends approximately 10 kilometers east-west. And it's an amazing place, and I'll show you a picture of it, of why it's important. When you put the earthquakes together with the hydrothermal features, you see the dominance of the east-west trend, this great cloud of earthquakes coming from the Hebgen Lake area. And by the way, this is the new location of the Hebgen Lake earthquake that we have just redone. It used to be plotted up here, down here. But nonetheless, there's this cloud of earthquakes that strings off to the northeast and one that comes down to the southeast. This is the northeast. And then they start to separate out into individual zones and belts. Now, this is a 1D location system. We've now finished the new 3D earthquake relocations, and these belts really tighten up as though they're active faults or fracture zones beneath the volcanics. I didn't have time to finish that slide. So here's the similar pattern. The color patterns are the hydrothermal features. I put on the stars of the post-caldera volcanic vents, 640,000 years and younger. There's a zone here in the Madison Plateau, and the youngest one is here at Fitchstone, 70,000 years. Another zone that comes down through here. And I put this in because I want to start explaining what I thought, how geysers work. And the whole idea is you've got a very fractured system at the top of the magma chamber, highly fractured both volcanic rocks and then unconsolidated rocks near the surface. And we get heat. I'll show you where the heat comes from. There's probably a brine layer, very dense, saline-rich water at a depth of about 1 kilometer that has its own circulation system, like in a coffee pot. It, in turn, heats the fresh water that comes in from the annual downflow of fluids from rain and snow and melt. And this is from geochemistry. You can't see these salt systems at the surface, but they can see the traces of them in the fresh water at the surface. And we know they're very shallow, 1 to 2 kilometers. So you have to see Old Faithful, of course. And that's, by the way, it's taken at 60 below zero the day I took that picture, middle of February with Rick Hutchinson. Old Faithful's been erupting since the day the first Indians came back to Yellowstone, and will probably continue. Here's Guardian Geyser, Midway, Upper Geyser Basin, and Behind Geyser right across from Old Faithful. I have to show these because these are the icons that bring people here. But I also have to show you this one. This is the biggest geyser in the world. Steamboat Geyser, and I have a picture of it erupting in 1984. I personally experienced this eruption because being a pilot, I had 2 photographers with me in an airplane. We'd been flying for 4 hours, flew out of Jackson. We were heading back to West Yellowstone because we're out of fuel, and they were out of film. July 6th. Now this geyser, as you can see, the highest in the world, at least 150 meters high. It erupts every 5 to 10 years prior to this date. And it lasts about 20 to 30 minutes. Now if you look carefully, you can see these are high-velocity steam vents that are shooting out. These are 70-foot high trees. Going back later, these were blowing out rocks the size of a Volkswagen. So we have hot steam jets to about 500 meters, and then steam rising, and then just a mist about 1,500. And then they fade away. So this is North Geyser Basin, and the parking lot is, well, the visitor center is right over here. Parking lot's right here in the trees. So it's right there where you can walk and see it. This is one of 10,000 hydrothermal features in Yellowstone. How lucky was I to get it? I calculated the probability of me taking the picture. 1 in 20 million. I mean, I can't fly at night. I don't fly very often. But this is the same as winning the Powerball lottery. So this is my Powerball lottery, and It is the only aerial picture of steamboat geyser eruption. Now, a few years ago, we had an Earthscope field trip. We led up Snake River Plain. A bunch of folks were, UNAVCO were with me. We went up the Snake River Plain, came to the Biscuit Basin. And Biscuit Basin is right here. And this is just south of north of Old Faithful, about a mile. And these are basins in here that have small geysers, hot springs, and fumaroles. But if you look at that rock, you say, how did that get there? Well, don't know. I had just lectured to say that earthquakes are rare in Yellowstone and volcanoes are even rarer. Dr. Hessler had just recorded that hydrothermal eruptions were rare and even rarer. So we were just sitting there thinking about all of this. There it goes, right behind our back. Now, Wade Johnson took this picture because Wade was behind me, right, Wade? You here? Everybody was back behind me. I'm seeing the election. This thing goes off. Holy hell. Was there a truck or an explosion? And these are rocks coming out. These are rocks. This is from a previous eruption, obviously, 6, 8, 10 diameter. So I heard the blast. I saw it, instantly considered, should I run? Do I have time? Get my camera out of the bottom of my pack, because that's where it usually is. I never take it. Or save my companions. I obviously saved my companions because the eruption stopped very rapidly. It's only a few seconds. But these are experiences of a lifetime working in Yellowstone. These are my Powerball wins. Well, this reminds me we got to get going here. I want to remind people that earthquakes occur in different forms. You mainly hear about a main shock, a big earthquake, and a lot of aftershocks. That's the common mode of earthquakes, and that's mode 1. It's captured in the study by Mogi, a Japanese seismologist who actually has the statistics of these systems, and he deals with the variable material types and the variable stress that are driving the faults that are rupturing. Type 2 have foreshocks. Now, these are the ones we hope we can use to predict the main shock. And, of course, this is the type of earthquake occurrence, small events occurring over some period of time, then the main shock and aftershocks. But these are swarms. Now, an earthquake swarm means you have lots of earthquakes that occur closely in space and time without a main shock. I mean, I truly say it's like a buzzing herd, a buzzing band of bees. They get a lot of little earthquakes and they die away. So I'm going to show you some new data on swarms. This is the map as of 2013.3. All of Yellowstone earthquakes are plotted here. We get about 800 to 3,000 a year. And the biggest earthquake in the whole Rocky Mountains was Hebgen Lake, 1959, killed 28 people. We get this intense seismicity that I've mentioned. The nearest intercaldera swarm is 1975 at the North Geyser Basin. And there's about 45,000 red dots on that map, which means we have a lot of recording, a lot of capability, and we're starting to use these data in a very sophisticated way. One of the intriguing things about the Hebgen Lake earthquake, it had 2 fault planes dipping to the south. That's surface rupture in red, dipping to the south. It created, in a Coulomb stress change calculation, an area of low stress, shown by the cool colors, and areas of increased stress shown in high colors. We call this the dog bone pattern. And if you're up here in this pattern, you decrease the capability of future earthquakes. If you're in here, you increase the capability of earthquakes. And these are plotted earthquakes I've shown right here up to about 1987 of larger magnitude 2s and larger. And you can see that indeed this earthquake sequence is filling in the dog bone as predicted. I'm going to show some more about it. Now, how hot is Yellowstone? When you go to Yellowstone, you wear nice warm clothes, right? Because it's a high alpine terrain. We have winter 7 months a year, sometimes 8 months a year. Temperature and the background temperature is cold. Well, we don't deal so much with temperature per se, but heat flow. And so heat flow measurements have been made in Yellowstone, and I just plotted some here by the bars, plotting out the value of heat flow units. And I converted these to watts per square meter. And there's a very high one at the north end of the lake, 35,500 down here. Up in the Absirica Mountains, 70 to 80, Snake River Plain, 100, Western Geyser Basin, 58,000, 41,000, 2,000. Yellowstone has a high heat flow, but not a high temperature. But nonetheless, it's the heat flow that drives the system. So we have roughly 2 watts per square meter of conductive flow and 500 milliwatts per square meter of convective flow. Oh, I'm sorry, convective flow greater than 1,500. 30 to 40 times the continental average. The annual output of this whole system is 6 gigawatts. And it can be modeled as the crystallization of about a 10th cubic kilometer of basaltic magma in the base of the crustal magma reservoir I'm going to show you. We made measurements in Yellowstone Lake. Each dot here is a thermal measurement. We take a probe, a Bullard thermal probe we borrowed from Lamont, put it down within 5 meters into the mud, and we measure the temperature, pulled it out. Well, I've just color-coded here the heat flux, kilowatts per square meter. Well, down in here you can see numbers that are around 3, 4, 500. And over in West Thumb, they start to get up, as you can see, in the order of about 2,000. Then as you get to the north end of the lake, look at that, it goes off scale. It goes off scale, it goes to 35,000. Here is a probe. We have a depth probe measuring temperature, both in Yellowstone Lake and several other places. And this is basically a reference point curve. Our depth probes show these temperatures shown in triangles and diamonds. And this is out near Mary Bay. Here's one at Stevenson. These are actually over toward Norris. The point being, if you stay left of that curve, you don't boil. If you go to the right side of that curve, you explode because of boiling. So here's the calculation of the temperatures at the boiling point for Yellowstone Lake. That is, this is the depth at which, up to 118 degrees C at this temperature and pressure, that we would see an explosion capability. Well, it's cool out here, it gets warmer and warmer. Look at this red in here. And the depths here are only about 3 to 4 meters. In other words, if you went in there and took 3 to 4 meters of water off the lake instantly, you'd have a hydrothermal explosion, a big one. Because this is Mary Bay, and Mary Bay is right here, 4 kilometers across. So there's a great potential for hydrothermal explosions in some places. Well, our seismic system consists of broadband seismometers, accelerometers, short periods, vertical short periods, borehole. This is the PBO borehole seismometers, and infrasound. And this is people maintaining the equipment. Here's a broadband at Lake. This is me installing another broadband. Here's one being installed right off the north at the end of Mount Holmes, and this is what they look like in the winter. We record send the data over to the Sawtail Peak FAA facility at Island Park, and I have pictures of 6 feet of ice on this whole system on some we had this spring. All the data come into here, and then they get onto the internet, and we get them at Salt Lake City via the FAA highly protected intra link. Now, what do we do with seismic data? I'm sure most people know this. I'm going to show you a picture of how we do a CAT scan. So we're going to put seismographs on the surface here. These are the black dots. And we're going to send seismic waves through the Earth. So they're propagating. These are seismic waves propagating 6 kilometers per second. And you can see the wave fronts. These are the wave fronts coming. But as they hit this body right here, they're being slowed down. They're being retarded because of slow velocity. Well, if you put enough of these together, of these waves, you can then outline this body by back projecting the time delay to the body that produces them. So this is seismic tomography. The problem is it takes thousands and thousands of earthquakes, different kinds, and very high resolution calculations. You guys are the first to see this. We showed it at SSA last week, 2 weeks ago. We just finished the new tomography for Yellowstone. So here are the stations in black. And you can see we cover the caldera very well. We cover the northwest caldera. And in the last 10 years, I had the vision kind of and got some money to install this station, this station, this station, this station, and this station to get coverage up here. And you're going to see why. 13,000 earthquakes had to be picked using cross-correlation and a training set manually for both PG, P-direct, and other phases. 159,000 observations, waveforms that are inverted. And let me show you what we got. Here's some slices. 2 kilometers, we're starting to see, this is relatively high velocity. We're starting to see some low velocity standing out to the west. 5 kilometers. Now we're starting to really see the low velocity of the central caldera. By 8 kilometers, we're seeing it extending further south. 12 kilometers, it's starting to subside. Well, these low velocity bodies extend from 5 kilometers to about 12. And we get this big low velocity body that goes well beyond the caldera boundary to almost to the park boundary. I'm going to show you the results. Show it is a major change with a velocity decrease of about 4, and in some places here 6% decrease compared to a reference 1D model. And we have a shallow low velocity body at 1 kilometer on the northwest side of Yellowstone. We think it's a gas-filled body. So here's what it looks like. There's a 3D cross-section of the what we think is the magma reservoir, 5 to 12 kilometers deep, shallowing markedly to the northeast, coming up beneath Mirror Plateau, and this is also a low velocity, but it's only 1 to 2 kilometers deep. Here's the map view. So you can see we almost go from the park boundary way out past the caldera. This is the new image of the magma reservoir. It's up to about 3 to 4% decrease in velocity. That corresponds to about 6 to 8% melt. That means you have like a sponge. 6 to 8% of the sponge has holes in it. This sponge has hot rocks, melted rocks in it. Well, here's some. We published this in '99. We didn't have very much data, but we knew there was something going on. You can see we had hints of low velocity beneath the caldera. Here's the gravity map, the Bugey gravity map, which shows this big anomaly, 20 milligauss to the northeast. And there's the body. So there's the image of the Yellowstone magma reservoir. And this was just jumped on by Discovery and Live Science and everybody else. And he's got to defend his thesis in 2 weeks, and we'll get it out. Here's the gravity data with that low velocity body. We inverted the gravity data. This was several years ago. We saw this same low density body and low velocity body, same location, Hot Springs Basin, Mirror Plateau. So the gravity data show almost identical structure. Now the next one we're doing is the combination inverting seismic data and density together for gravity. Now, fun thing about Yellowstone is that earthquakes happen all the time. When they happen, they repeat themselves. We had some in 1985 in the northwest caldera right here. Went on for about 3 months, and I'm not going to get into those. I'm going to get into these over here on Yellowstone Lake 2008, 2009. I'm going to talk to you about how these earthquakes occur. First of all, we had the ones on the northwest side of the Yellowstone Plateau in 2010. That's this cluster right here. Started in January, went on to February, March, April, May, June, July. We just had a big cluster at the same place last week. And these cluster in a very tight form, and these are both focal mechanisms and moment tensors. But the dominant feature is we have essentially components of oblique slip. But these are strike slip, Craig, sitting on top of this system. And this paper is about to be submitted where we've actually modeled it in 3 dimensions, and I didn't have the slides for it yet. But here's what the earthquakes look like. So the earthquakes repeat themselves. Look at them, they repeat themselves. But look at the times. These are tens of months and years apart. So the same source just keeps going off and off and off. And we now found this all over Yellowstone. Repeated clustered earthquakes. They can go for years. We just fit that particular set of data by some numerical, actually, modeling of viscoelastic fluids and temperatures, velocities, density. I can just say the best fit is a rhyolite magma. This one right here. And we actually were able to put in, calculate width of the dike, fluid pressure, et cetera, because we have all those structures from the data. What's interestingly is these repeating earthquakes, there's less if they're blue, there's more if they're red. As the caldera goes up, we get a lot of repeating earthquakes on the northwest side. As the caldera goes down, we get a decrease in the repeating earthquakes. As it goes up, we get an increase in repeating earthquakes. And it's Yellowstone-wide. The whole thing is shaking. And we think that this system, these things start out, they propagate from left to right here. You get an impulse of fluid, rhyolitic magma. You freeze the front of the fluid. We get earthquakes right out here. Then you get stress loading because you decrease the temperature and the stresses of the dike push it out. You trigger more earthquakes and this cycle goes on and on and on, and it breaks through. And if it breaks through, this is where you want to be to look straight down. So you guys that like to hike, this is Hot Springs Basin. I told you I'd show you a picture right there. 25 miles north of Fishing Bridge is Hot Springs Basin. This is an acid steam-dominated sulfate system. You do not want to walk across there without knowing your way. 3 USGS people in the last 15 years have had to be flown out because they break through and get scalded. You have to be very careful. Active sulfur is being deposited all throughout the system. And if you go a little bit further to the west, toward the canyon, you come to this place right here. Anyone been here? Anyone? Oh, you have? Totem Forest? Fairyland Basin? It's a hell of a place to get to. These are our spires. I mean, this takes 3 days to get into, and you can't take a horse. Look at this stuff coming up along the confluence of Broad Creek and Shallow Creek. This is an unbelievable place. And you can get a permit to go there. I'll tell you, it's harder than hell to get there, and it's even harder to get out because you have to go up 1,000. Look at this cliff. This is that Breccia Cliff all the way around. You've got to make your way down and make your way up. You can't do it in a horse, and you can't land a helicopter in there. This is the active part of Yellowstone. Okay, we know it gets hot and it gets cold. So here's showing you the temperature. This is a heat flow map for the Yellowstone Snake River Plain that was just published in a student thesis of mine. And we looked at the whole Snake River Plain and Yellowstone. We can see the increase in heat flow going from relatively high basin range numbers, as you can see about 100 milliwatts per square meter, up to Yellowstone. And I showed you this map to say the average heat flux in Yellowstone is about 2,000 milliwatts per square meter. 1 square yard produces 40 watts. So if you take some kind of converter out there, put your converter on the ground, you can convert the heat flow and light the light bulb in your tent. That's before the bear gets you. It's so hot that the earthquakes are extinguished as a brittle failure phenomenon. So if it's cool, it's brittle. If it's hot, it's ductile. And that temperature is at about 450 to 500 degrees. And I've plotted it here in cross-section, but here's the contour of it. So here's the depth to the brittle ductile transition. And you can see clearly the center portion of the caldera has the shallow, hot system. So we've taken the temperature of Yellowstone with earthquakes. But the focal depths have to be very well resolved, 3D relocations to do this. And I've told you already, the Total ductile transition is about 500 C. This requires 100 C kilometer gradient for the thermal gradient itself. It's 2,000 milliwatts per square meter. About 1,500 is in convection. Now, if you're following physical chemistry, that's a Nusselt number of 6. Y'all remember all these things, right? You learn back in physical chemistry and Rayleigh numbers and Nusselt number and Peclet numbers. If you haven't, you better. That's a very highly active dynamic thermal system. Here's some slices of the heat flow, because you can downward migrate these data, the potential field data, 3 kilometers, 5 kilometers, 7, and 10, leaving Yellowstone with this high feature right here. So Yellowstone has this very, very high conductive heat flux that's a result of fluids that are coming in from somewhere, the magma system. Now, I've already shown you that. 1973, I worked in Yellowstone at 53. I was a GS0. I think it was -0. I got paid $3 a day, I think. And I was a scientist technician's assistant. How low could I get? When you're that low, you can do anything you want. And they sent me around Yellowstone Lake, and I sampled the entire Yellowstone Lake system, the water system of rivers and streams, for chemistry, salinity, everything. I did all of Yellowstone Lake, all of Pelican, all of the western side of Yellowstone. I'd leave it Monday morning. They'd pick me up on Friday afternoon. I had a backpack, food. No maps to speak of, no GPS, no telephone, no cell phone. Just, Bob Smith, you're on your own. You better be here Friday at 5. That was always on my mind. I went down here. This is Peel Island, right at the south end of the south arm of Yellowstone. And there's a boat dock right here, which we had a fish egg station. This is Peel Island. It was one that had a fish hatchery on it. I went back in '73. Look at the boat dock. It's underwater. And you look out at this is how a biologist. This is a biologist testing his flies for cutthroat. I was doing science, but I looked across at all these these trees were dying. Now, why should all these trees be dying? There's no DDT out there. They're in the water. So I surmised that we had some kind of a dynamic phenomenon. If you take Yellowstone Lake and you tilt it to the south because of uplift to the north, then these trees become inundated and they die. And we discovered this in the 70s, and basically we used the lake shore as a bathtub ring. And I showed this to Bill Roney, who's a forest ecologist who maps in Yellowstone. He says, you just explained something to me. These are places he had taken pictures. These are all down on the South Arm, where all the trees had died. This used to be a peninsula. Now it's an island. So even the biologist gave me good supporting data for my hypothesis. So we started, and I said to myself, we better start doing things like geodesy. And in 1975, we started doing, this is Jack Pelton, one of my PhD students. We're doing first order leveling across the Hayden Valley. This is one of my recent PhD students. And here is the benchmark. Keep in your mind that benchmark has had the highest uplift rate of all of Yellowstone. And it is just north of Fishing Bridge, about 3 miles, the Hardy Rapids. This is what we discovered by going back to all the old benchmarks shown in the triangles here. They were put in when they built the roads for Yellowstone. They put in benchmarks, and they had the same kind of accuracy in optical geodesy as we do now. So we can go back with the same instruments, and these were NGS people who came back and helped us, and we resurveyed it. We picked this as 0, and as you march across Yellowstone, you can see 100, 200, 300, 400, 500, 600, 700 millimeters of uplift. We were surveying from Canyon this way, and I went back to the National Archives and got the books, the notebooks of these surveyors. So I wanted to see what they did. We were coming across about right there. This surveyor, the rod guy, the instrument guy, said, "Boy, these guys really made a mess back in 23. They're off by 20 inches." I said, "Sure enough, they are." And we resurveyed 2 loops in here to see if it was us. Took it back home that winter. This was the times of the Palmdale Bulls, right? Palmdale Bulls fiasco. Come on, you guys remember that. Southern California, the Palmdale uplift was a geodetic study that said the Palmdale Bulge was rising. Well, it turned out to be instrument related. So we got very careful. This gentleman, Jack Pelton, who's now the vice president of Boise State, he worked his tail off to prove that it was real. And there it is, 750 maximum uplift along the caldera axis. And if you go from right here at Lee Hardy Rapids, that benchmark down to Phil Island, by 1985, it was a full meter of uplift. Very active system, and you just don't pay attention to that in Yellowstone because the area is so big. Well, this picture here that Christine made for me of showing the uplift of that body between 1923 and 1977. It's both uplifting, but the horizontal motion is equally important. You lift something up, the sides bulge out, and she's able to calculate the Coulomb stress change, depths of 5, 10, 15 kilometers for the source of this. Now, look at that in your head for a minute. Let's go to GPS. On the left is the GPS network that we operate now, first by the University of Utah, and then PBO took over our stations. Boreholes are in there, borehole seismometers. We have campaign GPS sites. That's all the little green ones. They're hard to see. Of about 60 to 70 stations that we run. There's 100 channels of real-time data coming out of here. And this is what our GPS system looks like. This is our first permanent marker at Lake. Here's one up Upper Hayden Valley. Here's on top of Mount Holmes. North Geyser Basin. Lou, this is when you were there. Forgot who was there. Maybe one of you guys were there. Well, we do campaign and permanent GPS. Now, why do we put GPS this high? 12 feet, because we get 10 feet of snow. And we get 10 feet of grizzly bears standing up. And grizzlies have hammered this one twice. We're working in the field. We do a lot of portable studies. This is one of the first. This is the pioneer GPS person in Yellowstone. You recognize who that is? A little less hair, but same bright ideas, intelligence, and leadership. There we are, Chuck, up on Sour Creek Dome. Huh? Anyway, going back to the GPS, and we showed that by color here, 87 to 95, the whole caldera was going into a period of subsidence, shown by the colors of vertical, and the arrows for the horizontal pointed inward. We invert the source of the deformation. Here's the 85, by the way, 77. We see it's relatively shallow uplift. Then it was subsidence at the top of the magma body. 95 went into uplift. 2000 it went in subsidence. We were really struck. What in the hell? The thing just goes up and down and up and down. Then 2004, it took off. We have this accelerated uplift. Now I'll hurry up here. Here's a picture showing the earthquake distributions here, number of earthquakes, and over here the deformation. So here's the deformation pattern from 75 to 85 in a big earthquake swarm. Caldera went down, up, down, then really went up at 7 centimeters a year. That's a lot. Even in California, it's hard. And I plotted here the deformation outside of Yellowstone. It is over toward North Geyser Basin. When it goes down, north goes up, as you can see. And then red are the actual swarms of earthquakes that are occurring. But it's this one that caught our attention. And that's what it looks like. Both an INSAR image, GPS data right here. Red is vertical, blue is horizontal. These are the stations. They're inside the caldera, and it started going up late 2004. We thought the instruments were broken. David Drobeck made 2 trips to Yellowstone to see if our whole system had gone kaflooey. Well, you can see the uplift, and the maximum one is at White Lake, right here, 25 centimeters by 2010. That's a lot of uplift. It's so big it covers an area the size of Yellowstone National Park. So there's the INSAR image and the GPS on the DEM. You can see it almost goes to the west side of Yellowstone, up north of the northeast caldera. I like to use this picture because I live next door to the superintendent of Grand Teton National Park. And I said, if you don't watch out, I'm going to bring this guy down here. And we can fully involve Grand Teton, something like that. But that's an amazing image. This isn't Hawaii. When Hawaii has uplifts, you know, they're 5, 7 kilometers across. That's 60 kilometers inch. And the source is this inflating sill that's shown on the bottom here with a deflating portion over here. We have inflation of the whole body. This is the outline from the first tomographic image. Fluids are coming in. We interpret from a dike, and I won't go through all those numbers because I want to go to some more swarms. I want to go to this last big swarm, 2008 and 9. I happened to be driving from Salt Lake City to my home in Jackson on December 27th, I believe it was, and it was a hell of a blizzard. You guys have blizzards like we do. So I was about down around Evanston. Now, I have an alarm. My earthquake alarm triggers it everything over. I set right now -2. But I just reset it because we're running the new AQMS system. Here we're minimum magnitudes are 0. God, things are starting to go off. I wonder what's happening. Then it really banged, and there was a 2.1. Then more and more, and got up around Afton. This one went off, got into southern Jackson Hole, and the roads were closing, and there was a magnitude 4. This is for a station south end of the lake. Here's the other station over here. This is south end of the lake. This is up at Lake Wyoming. Look at the activities starting to be recorded. Thousands of earthquakes. And we recorded these things for a period of a week. We had great instrumentation. We found they started off with an explosive source earthquake that propagated from south to north, and the earthquakes got shallow from south to north. Now, the Park Service called an incident command system together because they didn't know, I didn't know, if this was an incipient something, an incipient big earthquake, an incipient hydrothermal eruption, or a volcanic eruption. We even have GPS data stations running, and here's the time scale. And we saw the deformation start roughly, if you look at the station here, lake, and here's the earthquake, then look at it take off. So either the GPS, now these are small displacements, admittedly, but they were certain, and we had to process them and come back and see them after the fact. Well, when things spread, it's probably because of a dike, and the whole idea then of this system being a dike filling with some kind of a fluid, of course, became a hypothesis. So earthquakes propagate south to north, shallow out. The earthquake, this one right here, moment tensor showed it was 60 to 70% explosive isotropic source. An explosion, not a shear. Well, you do that with fluids. And at that depth, it has to be magmatic. So we were testing these hypotheses. We had people on 24/7 for 1 week. Did we have migration of a highly pressurized fluid? Didn't say what fluid was. An elastic stress pulse? Or was it really a failed magmatic system? And I don't know yet. What I do know is that we were getting 10,000 web hits per hour on our data. 10,000. So this is as much as you guys get at UNAVCO, right, Jeff? I mean, this is enormous. for an organization, we're not that big. This was on the web, because everything on the, everything we have is real time. People were making beautiful maps and time, predicting explosions, et cetera, et cetera. So the public really grabs this information quickly. Now, this is the end of that kind of information. Just to point out in green, the total moment of deformation that's not seismic is about 1,000 times higher than the moment related to earthquakes. So earthquakes, while they have a relatively small moment compared to slow aseismic deformation, it shows you the magmatic sources are very important. And this is what we think we got then. A plume feeding fuel to the magma body, an extension, as you can see, of a body that's basaltic rich at the bottom, rhyolitic rich at the surface. I have to finish off with the hotspots, because everybody wants to know where they are and how they are. Here's hotspots I've known. You probably all know about Hawaii and the Cook Islands and Iceland and Union, Kerguelen, those kind of places. This is a fundamental part of plate tectonics. But around here, meaning the Rocky Mountains, a lot of people said, plumes don't come from the core mantle boundary. But they were in everybody's textbook. It said they come from the core mantle boundary, right? You guys were taught that. You probably still teach it. So this is Peter Vought's picture of that controversy. This was my idea. You had a plum, not a plume, something that was much shallower. Now, I remember all these mantle plume ideas by J. Tuzo Wilson and all the plate tectonics. There were, if you talk to Jason, he'll say, well, we just thought these things had to come from the core mantle boundary. Well, there were no images. Yellowstone was the first plume that's been imaged with the resolution to make the case I'm going to show you. First of all, if you have a plume that rises up, interacts with a North American plate moving from right to left, the plume comes up, it shears off, a depth of about 70, 80 kilometers, spreads out to the southwest. That creates, of course, this heat flow and the volcanic system of Yellowstone, of Snake River Plain. So we put out 80 seismographs, and we had 30 GPS instruments from here in a study that Gene Humphreys and I were the PIs on, and we ran them for 2 to 4 years, and the seismic stations are in red, GPS stations are in yellow. Most of these are campaign. Now think of a seismic survey as nothing more than an antenna looking down, right? That's all it is. It's like a radio antenna in your car. You tune it, and we wanted to tune this one to be north, west, southeast, elongated. Why? Because all the big earthquakes that come into North America come from the West Pacific. All the earthquakes that come in from the south come in from South America. Well, this is the Great Circle Path. So we wanted to get on tune with that path. 700-kilometer long network. Here's what we found. Low velocity beneath Yellowstone to a depth of 600 kilometers is the northwest-southeast cross-section. The velocity reduction up to about 2.5%. If you look on the right, there's no low velocity beneath Yellowstone directly. It goes down the Snake River Plain. So here's an isosurface, 1% velocity, and you can see the relative size. Here's Yellowstone right. Yellowstone's right here. There's the caldera. This is the Snake River Plain. This system is huge. So it's an isosurface of 1 to 2% partial melt, and it's deepest over here beneath the Idaho-Montana border. Now that got us really interested, and a lot of people came in during we were right before the TA array. Here's the new TA array data. So I'm working with Richard Allen and Proyd at Berkeley. He took all of our data, which were recorded at 20-kilometer spacing. The TA data are recorded at 75-kilometer spacing. So you understand aliasing in this group of people, spatial aliasing. TA data, spatial aliasing, because the stations are so far apart. But when we add our data in at 20, I'm not going to go through all these pictures, but they're put together. Oh, let me go back. And what you can see is this body well-defined at 100 kilometers, 200 kilometers, 300 kilometers. This body is still, or 400 as we did. We're starting at 16. We're starting to see a body over here to the north and east. And I'm going to show you a picture of it. Well, first of all, this is my body, our interpreted body, and you have return flow on the upper mantle causing the plume to tilt. We call it tilting in the mantle wind. And if you wanted to have a plume beneath Yellowstone, here's Yellowstone right here, it would have to start out here beneath Oregon because there's a convection cell beneath the western North America, and the ascent of the material, of course, rises buoyantly as entrained in the flow. So if you put a point here, it's going to come up here, turn, and there's where we image the plume, that orange body right there. Some work we're doing at Harvard. Let me finish off with just the statements here. That Yellowstone is a plume that's now shown below, I'm going to show you, 1,500 kilometers. Magma body is now well imaged. Earthquake swarms are the dominant mode of Yellowstone. And I'm going to argue that Yellowstone is always, always shaking. If you look at our network data at magnitude 0, -1, and 2, those repeating earthquakes don't stop. And that's because there are fluids that are migrating all the time. And these largest swarms, I'll show those. Yeah, this is my end. So here's the plume looking straight down the body. Here's the cross-section. It starts here. Here's the return flow. There's the low velocity body, 850 kilometers. Comes up, turns right. The mantle flow. We've just done an electrical image of the plume, and this is the image. Red shows the highly conductivity body. Orange is the plume. This is a brand new paper. It's just come out. These are using magnetofluoric imaging. And the system then is much, much bigger than we thought before. So these earthquakes across the north side of Yellowstone, the of an enigma, but I argue that the dog bone pattern of the Coulomb stress change, which is this area and this area, account for much of the seismicity of northwestern Yellowstone. And what's important when you look at the fault loading rates of that system, here's Yellowstone right here, here's the Wasatch. These are going to go on for hundreds to thousands of years. Because aftershocks are simply more than the stress unloading produced in these viscoelastic systems. Here's the repeating earthquakes. That's what they look like. They're all over the place. I mean, here's one right here. Here's a set down here. We've got a bunch down here. And you can see 2008, 2006, 2002, 1994. They're identical. They're identical because they have the exact same source parameters in the same location. And they're shaking all the time. And this is what I think, I've shown you what I think that model is. Magma intrusion, propagation laterally in the case of the big 2008 and 9 swarm. Now, one of the really neat things, when the caldera goes up, you get the big swarms, 1985 swarm. And when it starts to go down, it's the dashed arrow. We go back up again, go down, there's the dashed arrow. The big swarms precede these big period changes of caldera subsidence, which I think essentially, and we've modeled these, of fluids trying to get out of the magma, out of the caldera crustal magma body. So if we can see these periods of change from these GPS data and correlate them with these big earthquake sequences, I think we can start predicting when we might have magma migration. I showed you where the gravity anomaly was to the north, the Lamar Valley. And this is the body that I just showed you before. That's our newest result. Crustal magma body is a big system, as you can see, 100 kilometers long. The depth's about 15 kilometers. Now, one of the intriguing things, by the way, is that not only is it long? Here's the old magma body image. Here's the gravity image. Here's the new tomographic image. The distance from here to here is 20 kilometers. 20 kilometers is exactly the distance that the plate moves in 640,000 years. So we think it's actually contributing fluids as the plate's moving over Yellowstone, and the next big eruptions might be in Cook City or Billings. Here we go for how big and bad things are. Just want to finish off to let people know we deal with the public. Super volcanic eruptions, probabilities 0.00014% annually. And here's the risk where we take into account the area of exposure. Rhyolite flows. These are lava flows, you know. We've seen 60 to 70 since the last caldera. And you can see there, but they're small areas. Here's hydrothermal eruptions. There's a lot of those around Yellowstone, but they're tiny, except for 3 or 4 that are about 1 kilometer in diameter. But there's earthquakes. So annual probability is dominated by magnitude 7s and larger, and the annual risk is 97%. So Yellowstone is not a volcanic threat, it's an earthquake threat. That's what I want you to take home from that. Oh, it's always uphill. I've told you this before. A hot spot is 400 kilometers wide. And you can see it's about 40 to 50 meters high. That's right here. Where you drive into Yellowstone, you drive on top of the plateau because there's a hot spot. And that hot spot is produced by this body of magma that's coming up from the plume, leaking through, producing the magma reservoir, and this magma reservoir is producing some of the uplift. There's a lot coming from down here. This is low density. I just want to finish off here. I put these in because somebody might be interested. Yellowstone created a cold spot 2 million years ago. This is Yellowstone ice cap. 3,000 feet of ice. No one believed why. Well, it's because it's a hot spot, which means you have an adiabatic shift in temperatures by, as you can see, as much as 2 degrees to 4 degrees centigrade. This blue line here would be the last 2 million years of predicted temperatures, and here's what the hot spot did. So we're down 10 degrees from normal. Of course, here's what's coming back right now. So that's the effect of the hot spot. And all the ecologists, I have to get on their backs. There's what they defined. It's in every book. Guess what? It's just a hot spot. Smack on top the 6,600-foot contour. The Yellowstone ecosystem is really the Yellowstone geoecosystem. And thank you for coming. I'm up here on the top with my dog, which you can't see. I'm riding in the backcountry of Yellowstone. But I want to show you what I've done before I did all this. I was a pilot in the Air Force, and I got thrown into British Antarctic Survey. Here's some of the things we did in Antarctica. I know a lot of Antarctica guys. Cumberland Glacier. This is South Shetland or South Georgia Island. This one right here is the Palmer Peninsula, and this is Shackleton's grave. And I followed Shackleton's route completely out from the Bellinghausen Sea. We took those same dog teams in backcountry. We got big snowmobiles and dog teams, but we went out on the last trek. The last month I was there, we're back on the Yellowstone, on the glacier south of Halley Bay. This is about 50 miles to the south, and we have a dog sled. We're all roped. The dog sled came across the bridge. It broke. I fell down, caught myself. The doctor is down at the bottom of his rope. He had a camera in his pocket, took it out, shot up. He had a compound fracture. We got him out. Well, first he pulled me out. I broke my ankle. Then we got him out. Here he is. And we shot him with morphine, and me with morphine. I laid back on top of him with that same dog team. We went for 24 hours. Of course, Antarctica, it's always light. Saved everybody's life. Michael Thurston got the bronze medal from the Queen for that life-saving experience. I like to ski the high country. I know some of you guys like these. You know, Engelberg, I'm a professor in ETH in Switzerland. Here we are, we're going to ski this peak right here, right? We climbed up here, got on top, realized we can't see over that cliff. So we went up to the peak, sat down, and had a bottle of, come on, what's the Swiss white wine? Vendôme. Guess what? There's 3 PhD geophysicists here, and not one of them have a wine opener. So how do you open a bottle of wine when you've climbed for 6 hours? What? Come on, you guys must know that. There you got it. You take a ski pole, shove the cork down in the bottom, and consume it as needed. There we are. Here we are skiing places I shouldn't have been skiing. This is skiing Cedrone, right in the middle of the Alps, skiing up top of a pass down into this place. Skied that country for 2 days. Marvelous backcountry ski. This is the same crew we skied up to. We're heading for this peak. There's a hut up here. We skied up to the hut, stayed in the hut, and then we had to ski across this top of this bergstrom of this glacier. There's the peak we're headed to. Problem is, it goes like that. It's ice, not snow. So you take your ski pole and you push it out on between the ice and the rocks, take a step. And no ropes, because if you go, everybody else goes. So you all do it alone. And this hut was full of people, crazy guys drinking wine all night. We finally got over here. This is Jorgen Sword. This is me. We got over to here. And all these people came screaming out of the hut, put on their skis, right at, and here they are. We got up to the peak. Here they all are. You know what they are? Truck drivers. Do you think American truck drivers could do that? These are Swiss truck drivers down the Autobahn. Boy, in their time off, they're in the mountains doing pretty serious skiing. This is my last one here. I skied Mont Blanc, Guy de Requin. You've been to Mont Blanc, that's probably the highest peak in Europe, and we've skied that many times. And we ski off to the east and down into this valley, to this peak, Guy de Requin. We got there too late one morning, started going across, and there were avalanches between us and on top of it. There are avalanches like every 5 minutes, and so you'd ski between the avalanches, literally. There's an avalanche there and there. You ski there. And the guy was with me, he says, you follow my tracks to a millimeter. And I did. We made it. So the literal end is Yellowstone. My advice, visit Yellowstone before it visits you. I invite you to come and see me. And, of course, that's what Yellowstone looks like in real life, a new 3 tomographic image of the whole mantle, upper core data. That's what it's all about, guys. Thank you. Sorry I'm so long. So I know.
So Bob, Doan, 1870. So you showed us some snippets of his, his summary of what he thought was going on. But for 1870, those were totally crazy ideas. So what was the general reaction of the rest of the scientific community when he presented that?
He was stationed out of Bozeman, out of Fort Ellis, came down in the fall. I mean, in October, November, with his group. They made a boat, went across Yellowstone Lake, then they went down the Snake River, and it was, of course, freezing. And he made his way through, and by the end of December, they finally got out towards Pocatello and met some white people. It didn't kill him. He made his way back. his writings were done at a period when he was a lieutenant in the Army. Well, lieutenants in the Army have no status. It wasn't until Hayden came along, and Doan went with Hayden, and it was Doan who led Hayden to all the places that Hayden therefore took credit for that created Yellowstone National Park. There's a beautiful new book just come out on the story of Doan and his whole life. And he tried for his entire career to be the superintendent of Yellowstone. And because he had done this he led these guys, almost killed them all, he was not allowed to become a superintendent. You remember, Yellowstone became under the jurisdiction of the U.S. Army in 1890. And Doan was there waiting to become the superintendent. And he was disallowed by Washington, D.C. And the answer is, you see his writings after the fact. You don't see them. I mean, I found them after the fact in a couple of books. But the new book just came out, has all of the stuff. It's a pretty dreary story of the U.S. government and how they squashed the military and how they hyped the Dr. Hayden. Because it was Doan that was doing the work amongst a few others, and Hayden got all the credit. Mm-hmm. Whoa, well, you just had a meeting last week. The TA array is now on the East Coast. Of course, the Mineral Virginia earthquake of 2 years ago sparked, y'all familiar with that? Magnitude 4, Mineral Virginia. Shook the hell out of Washington. Congress failed, it did a lot of damage. So Congress has given the USGS, they're going to give them $2.5 or $3 million to buy 160 of the existing TA stations that are in the ground, and they stay. So Earthscope's right in the mode of buying to make those replacements. They're going to Alaska starting not next year, but the year after. We're going to, and what we're testing for them, borehole broadband seismometers that just came into being. We're going to go in Chuck's boreholes, we hope, and test these new borehole seismometers, because they want to use borehole instruments a lot more in Alaska than they have. The answer is, I think they're going to get some beautiful data in southern Alaska, no question, you know, on top of this subduction zone. And but it's going to take them a long time, and it's going to cost them an enormous amount of money for logistics. But that's kind of Earthscope 3, and we don't know what's going to happen with that total funding and how Earthscope's going to be treated, you know, within NSF. NSF tends to like to have these programs mature and then turn the switch. But Earthscope as a whole, I think it's done so well that it'll probably likely get some reasonable funding. And of course, they want to integrate all the GPS in as well. And they want to do joint flights and joint reconnaissance for GPS and seismic. Expensive place to work. I think it's going to be a great opportunity. You going to go? You hope so? Any more?
Well, thanks, everyone. And thank you, Bob, for this excellent presentation. Let's give him a round of applause. Thank you.
Sorry I was so long, but